Okay, let's Lechatelier principle. Okay, let's just see what is this principle. It states that a system of equilibrium, when subjected to a change, will respond in such a way as to minimize the effect of the change. So this is something that I always talk to you in this course. You make a change when nature doesn't like it. Okay, you want to go back to equilibrium. You disturb something, it will try find a way to get everything back to equilibrium and establish a new equilibrium. Applying the Lechatelier principle enables us to predict qualitative effect of typical changes that occur to system at equilibrium. So you have this worksheet at the front. Please grab one if you're just arrived. So let's just look at that. Yeah. Adding or removing a reactant or product. See what is happening to this. So we have Fe plus reacting with SCN, giving you FeSCN, and you want to see if you add reactant. Okay, Fe, if you really add more Fe to the system, the nature doesn't like it, right? What do you think the shift will be? Do you think this reaction um, shifts forward or backward? Why? Yeah, it doesn't like it. You need to consume that, right? So you need to go forward. So you shift that to forward and then establish a new equilibrium. Okay. Now, removing reactant. Now, it is you taking some Fe away. What do you think the shift will be? Toward? Is it going to be forward or backward? If you remove Fe. Yeah, because you remove it, the nature doesn't like it. You need to produce some. It's going to be backward. Now, removing product. Here the product is FeSCN. If you remove that, take it away, what will be the shift? Forward or backward? Forward, because you remove it, right? So you remove it. Nature doesn't like it. So you have to shift forward to make some of that. It's going to be forward. Now, I want to use another word for that. So adding reactant, shift the reactant toward, because this is forward, is toward product, right? And backward means toward the reactant. Again, forward is toward products. Any question? Okay. Changing the volume of the gases. Let's see if we change the volume, what happens to this? The reaction will move in a direction that produces the least number of the molecules in the pressure. If the pressure is increased. Okay, let's just talk about the pressure increase. Okay. If you increase the pressure, what do you do to the volume? Do you increase the volume to increase or decrease it? You decrease it, you put pressure, everything getting very tight together, right? So increasing pressure, it means you decrease volume, right? So increasing pressure, you decrease the volume for that. And Where do you think this reaction shift will be shifted? So forward or backward? If you decrease the volume, you have less space, right? You have to accommodate for that less space. You depressurize, if you want to say that. Do you bring more people to the room, or do you kind of put people together and make tiny things? What do you do to depressurize? Okay, maybe I ask you, how many molecule do we have on right side? Two, and it's in gas form. And how many molecule do you have in left side? Four. If you really have a little room, which direction do you go to uh come up with the solution of having a lot of pressure to depressurize, or the right side? Just think about it. You have a room. Now your room is smaller. Of course, you want to have two in a room rather than four, right? Okay, so it will be shifted towards the product, or it will be shifted to the direction produce least number of molecule, right? Again, the pressure increased or the increased or the volume decreased here, and this will shift forward. Okay, a decrease in pressure. Okay, look at the second one. Now you decrease the pressure. So pressure is going down. Oh, sorry. Yeah, decrease in pressure will be increase in volume, right? Now, it's favored the side with uh the largest number of molecule, right? Or higher. Which is will be shifted to the right or left? Yeah, or backward, right? So backward. Now you have more room or more space, so you can have more people or more molecules there. Shift backward. Okay, next one. If there is no change in number of molecules on either side, look at this. How many? So H2 plus reacting with I2 give you 2 HI. How many molecule do you have on left side? On right side? So there is no preference, right? Now, if you have no change in the number of molecule on either side, so 2 at the both side, you change the volume on pressure has, what do you think here should be? No effects. Very good. Any question before I move on? So we did adding, removing reactant. How does it shift your equilibrium? Change in volume. How does it shift equilibrium? And now we want to do change in temperature. How does it shift our equilibrium? So here is the Haber process. Nitrogen and hydrogen gas react, give you niche free. So the delta H is negative 92. It means, is it exothermic or endothermic? Exothermic. So the heat will be on the right side or left side? So exothermic means producing heat, right? So you will have the heat on this side. Okay? Will be produced. The heat will be produced because it's exothermic. Now, at low temperature, do you think this will be shifted forward or backward? So low temperature, the nature doesn't like it, right? Because you lower the temperature, now you wanna Pardon? Okay, so you have to go forward or backward. Just if you go backward, you're taking heat from space, so it become colder, right? So you have to go forward, producing some heat to warm it up, right? That's low temperature. So you have to go forward. So it's going forward. A low temperature, you're going forward. Just put it at forward. But forward reaction is exothermic, right? At high temperature, what's gonna happen? Is forward or backward? Backward. High temperature, you don't like it, you wanna just lower that. So backward will absorb some heat for you, which is endothermic, and it's gonna be backward. Okay. Now we want to talk about effective catalyst. Okay, a catalyst will reduce the time that the reaction gets to equilibrium. So that doesn't have any effect on the equilibrium, right? No effect. It's not shifting, but it's helping that to reach the equilibrium faster. Okay, so it does help reaction reach an equilibrium faster. And I'm gonna put a picture here. If let's say this is what you have, um, here you have product. At the beginning, you do not have any, right? So it will be produce increase, and then after some times, it will be constant. When it become horizontal, it means you're reaching equilibrium. I just put this EQ established at a point when nor your product changing, nor your reactant changing, right? That is equilibrium. How the catalyst help you? It help you to reach equilibrium faster. Okay. Um, maybe I just do it in a different color. So it will be something like that. Okay. Very fast. Okay. You're reaching equilibrium faster. Your curve of this will be a little bit sharper, right? So the rate at which reach the equilibrium going to be faster. I'm going to make some picture for the above reactions. That would be nice if I do some here. And tomorrow we'll go over this graphing. When you change something. Let's say I suddenly increase FE, right? So see at the beginning, I have some FE and I have some SCN, right? And maybe I don't have any product, which is FeSCN. Okay? So I have some reactants. So on the y-axis is amount, and I don't have any product. I'm gonna use the different color for each. Let's just do Fe black. So what happens? The reaction starts, so Fe go down and it become constant, right? Also SCN go down and then become constant. At this point, when it become constant, the equilibrium is established, right? And then what happened to the Fe? Fe go up and become constant at equilibrium. So this is things happening. But let's say you suddenly put some Fe into the system. You increasing, you just disturb this. What happened? It suddenly jumps, okay? And after it jumps, because you said the reaction will be shifted forward, jumps, but it need to go down and then again establish new equilibrium. What happened to the SCN? You didn't increase SCN, right? So and the reaction goes forward, so it just go down and then become constant, equilibrium established. And because you're producing Fe, it's a little go up and get to a new equilibrium. So let's say my new equilibrium will be established somewhere like that. I want you to pay attention. You are putting some Fe, right? You're dumping some Fe into the system. That's why you see you jump here. But the rest of the entities here goes normal. If you is jump, but you go down because the reaction go forward. This is go down because the reaction go forward. Let's go a little bit up, reaction go forward. And again, you will have a new equilibrium. For sure, I will give you a question like that in your test and quiz to draw such a change. Show me you know how to do this. But I believe we will work on that later. Uh, just introduce you to this. And right now, I want to do this quantitative aspect of the Lechatelier principle. And then I will give you some time to work on question number 1 and 2. And perhaps I will explain number 3. I will do one of these charts for you. The other chart, you can fill it out yourself. Yeah, okay, that's the plan. Okay, let's do this. Okay, we want to calculate the concentration of a product when equilibrium has been disturbed. Okay, this is an example. Analysis of an equilibrium mixture represented by the following. We have SO2 plus NO2 give you SO3 and NO. So they are in gas state. The equilibrium concentration of each is given to you. What is the new equilibrium concentration of NO when 1.5 mole of NO2 is added? So it's already at equilibrium. You want to disturb this. You're putting 1.5 mole of NO2 into the system. Is added to a liter of the first mixture. So I don't see my K equilibrium because I think at some point I needed that. Where is that? Can I find it? How? Exactly. We have equilibrium concentrations. I can use it to find it. So KEQ, let me just so KEQ is product is NO and SO3. The power is 1 because the coefficient is 1. Is that balanced? I didn't check. Yeah, it seems to be balanced. So it's 4 here, 4 here. 1 is okay, it's good. Divided by the reactant, which is SO2 and NO2. If we do that, NO is 2, SO3 is 3, and it's already concentration. Don't need to be worried about that, right? So it's 4 and 0.5. Okay, the number will be KEQ will be 3. Now I need to establish the ice table, right? Before I do that, if I add NO2 1.5 mole of NO2 to the system, what will be the direction of this reaction? Will be shifted forward or backward? You're putting more NO2 here. You have NO2. The system doesn't like it, right? The nature doesn't like that, the change that you did. So you need to use it up, right? To use it up, do you go forward or backward? Forward. So keep that in mind. This will shift everything forward. When we do ice table, we need to make sure we know that. So it's SO2, SO3, ice table. Initially, change equilibrium. So initially we started with 0.5 mole per liter. Here is 3 mole per liter, and here is 2 mole per liter. Now the change, since you set it forward, so that would be minus x. That would be minus x, plus x, and here's plus x. But there is another change, 1.5 mole of NO2 in 1 liter. What would be the change in molarity? Addition to the negative x, I need to say this change here, right? You plus it, right? So plus, just maybe I just put that there in with different color. So that would be 1.5. And make sure this 1.5 is mole per liter because I did that divided by 1 liter, okay? 1.5 mole per liter. I just put that here. Mole per liter is change. Okay. Now at equilibrium, we have 4 minus x, 1.5 minus x, 3 plus x, 2 plus x. Now the rest is easy. You just need to use the things, KQ. So again, we're using the same thing. Now KQ is 3. Yes? This one?
No,
Okay.
I'm not like, wouldn't it be at equilibrium would be 2 minus x, not 1.5? Because they're adding. Or 0.5 plus the 1.5.
Oh, okay, yeah. Thank you. Thank you so much. Yeah, absolutely correct. Thank you. Okay, thanks for correcting me. Actually, I didn't realize I have to do this. Okay, maybe I just check everything. Okay, good. Now I'm gonna establish this KEQ, the product over reactant, 3 plus x, 2 plus x, products go on the top, and you will have the reactant here is 4 minus x, 2 minus x. Okay, I need to expand this. Let's do that. So that would be 3. It's 3 plus x, 2 plus x. Um, x power 2, x power 2 plus 5x plus 6, 3x2. So what I did is, I think I did something wrong. It's going to be 8 here. Um, so that's going to be 2x2. Uh, minus 23x, um, 18, right? So x1, x2 is 23 plus minus the square root of, I really need my calculator. There is no answers here, but that's okay. B power 2 is negative 23 power 2 minus 4ac divided by 2 divided by 2. Okay, I need my calculator. Oh, thank you. Okay, so it's 23 x square root of 23 to the power of 2 minus 4 divided by 18. That's it. Okay. Yeah. This is 21. Okay. So this is 21.4. I just round that. So 23 minus 21.4 divided by 4 is 0.4. One of the answer is 0.4. Another answer is 23 plus 2.21.4 divided by 4. It's going to be 11. Okay, so of course the 11.1 not going to be acceptable because if 4 minus 11.1 doesn't make sense. It would give you a negative, and 0.4 will be accepted. Here, 4 minus 0.4, 2 minus 0.4, 3 plus 0.4, and 2 plus would be 3.6, 1.6, 3.4, 2.4. It's going to be mole per liter, right? So these are the concentrations at equilibrium. Instead, what is the new equilibrium concentration of NO? We need to, yeah. Which, okay, maybe I made a mistake, yeah?
It was just in your calculation on square root part.
Oh, yeah, okay, I do it again. Okay, I do it again. 23 power 2 minus 4 multiplied by 2 multiplied by 18. So, oh, okay. Yeah, it's okay. Thank you for correcting me. It's 19.6. Okay, 23 minus 19.6 divided by 4 is 0.85. Did you get 0.85? Yes. Okay, thank you. 0.85, and it's 23 plus 19.6 divided by 4 is 10 point. I just got that. It's 10.65. Gonna raise this values then. Da, da, da. Okay, here is 0.85, 0.85, 0.85. I'm gonna change my color, I guess, for 0.35. Okay, 3.15. 2.85, 2.85. Okay, so this is mole per liter, or just put the molarity here for sake of I don't want to write it. Okay, so this is not acceptable and you accept that. I'm gonna just stop my recording right now.